Okay, this is going to be part 5 of this October 2024 Unit 5 exam from Edexcel International A-Level for Physics. So it goes through thermodynamics, radioactivity, what else is in there? Cosmology. There's something else. I can't remember what it is. Anyway, you'll have to look at the front of the paper. So thank you if you've watched the first 4 parts. If you haven't watched them, they're in the same playlist. Go back and have a look. Like each video, give me a thumbs up each time. It's how you pay me. I do the work, you give me thumbs up. So for those of you who are watching and not giving me a thumbs up, where's your good manners? Okay, so that's what I expect. I show you the videos, I do it for free, and you give me all the positivity you can and share it with your friends. Increase my subscribership. I've got over 100 in the last week or so because of everyone wanting to get ready for the units this week. Okay, so I've squeezed in this Unit 5 for you. Not currently teaching Unit 5. My students don't do it till the summer, so it's for you guys. So that's what I expect. Everyone who watches it, I expect you to give me a like, I expect you to share it, and I expect you to say thank you very much. Okay, so as it gets later in the evening, and I've been up since 5 o'clock this morning, I am now doing question 17 for part 5 of this video. It says, and I read, Arcturus is a red giant star. So what does that mean if it's a red giant star? Well, when the spectrum of radiation received from Arcturus is analysed, the spectrum is found to be shifted compared with the radiation received from the Sun. Now, obviously, all suns, all stars will produce certain frequencies due to the fact that they're all kind of made of the same stuff, hydrogen, helium, etc. Now, the red giant star will be more into fusing helium than our sun, which is fusing hydrogen. But they're saying that there is a comparison between the wavelengths. Now, this is a redshift question. That means the wavelength has increased, and that means that, in short, Arcturus must be moving away from us as the observer. Okay. Just taking a sip of my drink. Part of the spectra of radiation from Arcturus and the Sun is shown. And you can see I've put, looking at the wavelengths, I have put the value of the 2 peaks that they're comparing. So for Arcturus, it's exactly on 884.0 nanometers. The same peak for the Sun is 883.85 if you read the scale accurately, and they're deliberately making it not so easy for you to compare them. You need to be able to look at the 2 wavelengths and see how much is shifted in Arcturus, and that shift red towards the red end of the spectrum tells us that that source of light, in this case a star, is moving away from us. Okay, it's the Doppler effect. So it says, explain why the spectrum of the radiation received from Arcturus is shifted as shown, where Arcturus must be moving away from the observer. Yes, in other words, it's receding, and this motion causes a Doppler shift such that the observed wavelength, or received by the observer, is increased or perceived to be increased. So the wavelength goes up, and those are the 2 marks. The underlined bits are the bits that you get your marks for. So that's part A. Part 1, part 2 says determine the speed of Arcturus relative to Sun. So you need to read the scale, which I've shown you on the graph before, to determine the change or the shift in the wavelength. So use the graph to determine lambda and lambda dash, the shifted one for Arcturus, accurately. See my graph, which I've just shown you. Calculate the change in wavelength. Delta lambda means the change in wavelength. So you take the smaller number away from the bigger number. And remember, it's nanometers, so it's 10 to the minus 9. So once you do that, you will see that the change in the wavelength is 1.5 times 10 to the minus 10 meters. And the equation that you should use is this, which is given to you in the back of your exam sheet. The change in wavelength over the original wavelength is equal as a ratio to the receding velocity v divided by the speed of light. So the only unknown, as we know what c is, we know lambda, and we know the change in lambda. The only unknown is v. So you should be able to work out that v is going to be the shift in lambda divided by the original, which would be the value on Earth, which is not moving away from us, hope not anyway, and multiply it by the speed of light, and you will get the receding speed, or the speed of recession, which to 3 significant figures is 5.09. You should really round that up, because we don't know things that accurately to 2 significant figures, but either of those I think would be satisfactory for this question. Okay? All right, so that's how you do recession velocities. It then says, for the end of this question, when light from galaxies is analyzed, remember we're just looking at one star in Arcturus, which is in our own galaxy. A shift towards greater wavelength in the spectrum of radiation is observed. Well, if the Arcturus is moving away from us and the redshift is observed, also greater wavelengths means that it is also redshifted, because greater wavelength is towards the red end of the spectrum. Yeah. Describe how astronomers use a knowledge of these shifts, redshifts, to determine the distances to the galaxies. Now, so to determine the distances from the redshift, well, the method above is used for distant galaxies. You work out the shift in the wavelength, and from the shift in the wavelength, recession velocities are determined. Yes? So they're determined, or you could say calculated, yeah, using the delta lambda, as I've done above. That gives you 1 mark. And then you can use Hubble's equation, which is given to you in the formula, V equals H naught D, where H naught is a known value, yeah, the approximate link to the age of the universe. And once we know what the accepted value for H naught is, and we know V, we can then determine the corresponding distance using the Hubble equation. Okay? It's called Hubble's law. And that's the end of this question. So a reasonably straightforward question for a question towards the end of the exam. Remember, questions at the end of the exam tend to be more difficult. Let's have a look at the mark scheme, see if I've got the mark scheme here or not. Yes, there it is. So if you want to pause the video for a while, I'll stop talking for a minute. You can have a look at it, and then you can pause it, and then you can come back and we'll do question 18. Okay, another sip of my drink. Question 17 done. On to question 18. For those of you still awake, depending which countries you're from, while I'm taking a pause between the questions, it'll be nice for you to comment as to which country you're in. As I told you in a previous video, or told those of you who were listening, that the number 1 country in terms of my audience is, or viewership I should say, because they're not just audience, is Bangladesh. Bangladesh is number 1. UAE, where I'm working, is number 2. And then some other countries in the Middle East as well are near the top. So let me know which country you're from. Obviously, there's quite a few countries that it reaches. And for those of you who know or have friends who are doing linear, I'm starting to do linear EdXL exams and upload them as well, because I'm going to be moving away from modular into linear from this year. Okay, that doesn't mean I will not do any of the modular exams, because I think the modular exams are very good practice even for linear students. And if you're doing linear, you only get the exam in June, whereas if you're doing modular, you got June, October for resits, and you've got January, so it's 3 different sittings, so you get 3 times as much exam practice. Okay, so without further ado, here's question 18. It says, in the 17th century, Galileo observed the planet Jupiter. And if you have ever looked at Jupiter, you can look at it through binoculars. You will be able to detect, with good binoculars on a clear night, you will be able to see 4 moons of Jupiter. Okay, so he observed it through a telescope and discovered a number of moons orbiting the planet. Galileo made observations of the movement of these moons for 8 days. So this question is relating to these 8 days. Was it long enough to observe it for his conclusion? The largest moon is called Ganymede. Deduce whether 8 days would have been enough time for Galileo to be sure that the Ganymede was orbiting Jupiter. Okay, so they've given us some stuff. Radius of orbit of Ganymede is given, 1.07 times 10 to the 9, and the mass of Jupiter is given, so that's a big M, and 1 day is given in seconds just to save you from working it out, save you time. Now, for anything which is orbit, we're talking about centripetal forces. Okay? Now, centripetal forces is, in this case, due to gmm over r squared, which is Newton's law of gravitation. Yeah? So you can equate this centripetal force equation, which is mr omega squared, or the other version. Well, we want omega because we're talking about periods of orbit. And you can see that the mass of the moons cancel out, and all you need to know is the mass of the planet they're orbiting, in this case Jupiter, which we know is given to us here. Okay, so we know the mass of Jupiter, and we know the radius of the orbit r. We know the universal gravitational constant, that's big G. It will be given to you in a data sheet at the back of the exam. So we can simplify the equation and come up with a new equation, which is very useful, as omega squared equals gm over r cubed. Now, this is very close to Kepler's equations, except Kepler changed omega using this equation to work out the time period. Okay, so this equation comes from centripetal force. Yeah. So once we know that, we can work out omega squared, and then we can square root it. So if you square root this number over there, you will get 1.02 times 10 to the minus 5 radians per second. Now, if you know the omega, it's not difficult to work out, well, it shouldn't be difficult to work out the period of orbit, but I nearly made a mistake. I put my equation upside down. Okay? Now, believe it or not, I had a GCSE student this week who they were given a formula sheet and he simply copied down the equation wrong. Now that I see my own error, yes, I can see how easy it is to make a mistake when you're under pressure. Okay, well, I wasn't under pressure. I just made a silly mistake. So you can see I put the numbers upside down, so I've now turned it round. 2 pi over what we just worked out, which is omega, gives you the period of 6.18 times 10 to the 5 seconds. Yes, so that's more than 1 day. Well, how much more? So if you divide it by this number here, you can work out how many days it is, which is what I have done. And when you divide it by the number of seconds in 1 day, you'll see that it's 7.15 days. That means the time for it to orbit Jupiter will only be 7.15 days. So 8 days observation, yes, will be sufficient. I don't like the way I did that. Let me get rid of that. I don't know why I did that. 8 days of observation of Ganymede will be sufficient, as 7.15, the period of orbit, is less than 8 days, which is the number of days of observing it. So it would have completed an orbit fully, and therefore Galileo would have been able to determine that it was orbiting. It would have come back to its starting point and more. Okay, so that's how you write your conclusion. The ticks are where the mark scheme says you get the marks. Here is what we just done, part A. Here's the answer for part A. Okay, I'll let you pause, have a look at it, and then you can stop the video whenever you want, and I'll come back to you to do 18 part B when I've had another sip. So don't forget to tell me which country you're doing your exams in. It's just out of interest. Okay, we've kind of got a community here now. We've got 800 and something subscribers. I'm sure some of them are no longer active, because I bet you some of them are from last year and they've already gone to university. Yeah. As I said to an earlier video, one of my students from China, he was watching, he came back to me after he got his grades and he said, "Thank you very much, I got an A." I didn't know who he was, but he obviously had used my channel and it had helped him sufficiently for him to remember it to come back in August and say he got an A. Well, that's why I do it for free. Okay, hopefully one day I'll get paid for all my efforts. All right, so 19 also coming up, but I don't think I'm going to do 19 in this video. I think it makes them too long. So here's part B. It says, show that the gravitational field strength at the surface of Ganymede is about 1.4 newtons per kilogram. Well, to be able to work out the gravitational field strength, you have to use the correct equation, which is this one. Okay? G equals gm over r squared. Well, we know r, we know m, so we can work it out. You just simply put the numbers in. You can see capital G is 6.67 times 10 to the minus 11. 1.48 times 10 to the 23 is the mass of Ganymede divided by its radius. Don't forget it's kilometers, so you've got to change it to meters. And once you do that, you can get to 4 significant figures an accurate value, which is what I quoted to, and then I show you to show the question that's about 1.49 because they want it to be about, and in this case about is to 2 significant figures. Yeah, so to 2 significant figures we have shown that it is what they've asked us to show. Okay, next part. It says the radius of Ganymede is about 50% larger than the radius of the Earth's moon. So immediately I put, well, the radius of Ganymede must be, if it's 50% bigger, must be 1.5 times the radius of the moon. Okay, so they're going to want us to do some algebra. Explain what can be deduced from the mass. It can be deduced about the mass, it's getting late, about the mass of the Earth's moon from this information. Well, we know, it says, the gravitational field strength at the surface of the Earth's moon is similar to the gravitational strength, so we're saying it's approximately the same. So we're saying that both of them are going to be 1.4. If we can't do that, we can't solve it. So that means G for both of them, which is gm over r squared, should be 1.4 for both of them. Okay? So one is for the moon, I put mm for the moon, mg for Ganymede, rg for Ganymede, rm for the moon. So we can cancel the big G's out. So the ratio of the mass to the radius squared should be constant. Now we want to work out the mass of the moon. So if we change the subject of the equation, we can say the mass of the moon must be the mass of Ganymede multiplied by the ratio of the squares to put in the correct form. Now it's just changing the subject of the equation to make m, the mass of the moon, the subject of the equation. And you'll see that you can then replace for Rg, you can put 1.5 into there, Rm. So you're basically replacing this squared value, you're putting in this instead of Rg and squaring it. Now 1.5 squared is 2.25. The M's will then cancel, so you get rid of Rm there and Rm there, and you're just left with the 1.5 ratio squared. Therefore, the mass of the moon must be the mass of Ganymede divided by 2.25. So you can put the numbers in and work out the mass of the moon. Yeah? Actually, I was teaching my students in Year 7 today about forces, and I told them the mass of the Earth and why, small objects like golf balls will move towards the Earth rather than the Earth moving towards a golf ball. And then we talked about the gravity on the moon compared to the gravity on the Earth, and I could not remember, even though I just done that question, I couldn't remember that. The mass of the moon, 6.6 times 10 to the 22. Okay, I always remember the Earth's math. So the Earth is nearly 100 times more massive than the moon. Okay, so I think that's a good place to stop. Let me just show you the video. So don't forget, like, share, subscribe, and tell me which country you're in. And there is second part of, what are we doing? 18. Second part of 18, 18B1 and 18B2. So I'm going to stop the video there. Thank you for watching. Catch you in the next video. Don't forget to subscribe and make sure you get notifications switched on. Okay, bye for now.